Hey everyone, so this is a video that's going to explain the commonalities between the Lagrange Remainder Formula and Taylor's Inequality. So here I've got Lagrange's Remainder Formula, and I describe it in my slides, and I'll talk about it on July 16th, that's a Monday. And hopefully the plan is to use it to solve 7b. From assignment 9. So this is assignment that was already due, but we talked about in class in terms of how to do it. So let's talk about why that was true. What I'm going to do is I'm going to, in this video, get to an alternative form of Taylor's inequality that is more useful for you to use, and then I'll show you how the one that I showed you earlier is still actually true. So alright, let's get to it. So in an effort to make it look like Taylor's inequality, I'm going to take the absolute value sign. So here, everything else has an absolute value sign. The k plus 1 factorial, well, that's always going to be positive, so I don't really need one here. Times x minus a to the k plus 1. Great. So this looks a lot like Taylor's inequality. The only thing is this thing on the top is usually replaced by some sort of m k plus 1 thing. Alright, so let's deal with just that piece and see what's up with it. So we've got f of k plus 1 to the c. Alright, so we know c is some number between x and a. Right, so I'm just going to draw a picture. Draw out a picture. It's going to be of some sort of function. And that's not actually a really nice looking function. Let's try something else. Alright, great. So that is of another function. So let's say, for example, our Taylor series is centered at a. Right? Our Taylor series or Taylor polynomials are centered at a, so we have some value for a here. We care about this function inside the radius of convergence. So we're going to have a radius of convergence, so a plus ROC, which that shouldn't be a minus, plus ROC, and we're going to have some value here, a minus ROC. Alright, so let's say we have an interval for where our Taylor series would converge. So for example, you can think of you can think of the sum of n equals 0 to infinity of x to the n. And we know this is equal to 1 over 1 minus x. Right? And we know this is true for x less than the absolute value of x less than 1. So we can use the Taylor polynomial to approximate this, right? We can just take a certain number of terms to approximate this, but this would only make sense inside the interval -1 to 1. So if we try to do it outside of the interval, then it's all hell will break loose and it won't actually work. So here, if I take a, so a is in my center, x I would pick to be inside my interval of convergence, because otherwise it's not a good approximation, it just doesn't make sense. Sometimes you'll have an interval of convergence that's infinite, right, negative infinity to infinity, and that's fine, then you can pick x to be anything. So here, I'm going to pick x to be inside here. So the whole point of me rambling on about this was that c is between x and a, so obviously I'm going to pick a point c that's in between. Alright. So the point here is, if I evaluate this function at the k plus 1 derivative of f at c, let's just pretend this is the k plus 1 derivative. It's just a function. So if I evaluate the function at c, then that's got to be less than or equal to the maximum of this function between a to x. Right? So I'm just going to write here it's the same thing, k plus 1 evaluated at c. So it's between here to here. Well, the maximum is over here, so this inequality was true, right? Yeah, proof by graph. But anyway, if you want to, try to convince yourself, draw a couple different graphs, and you'll always see that this is true, right? It's just saying that the maximum across an interval will always be bigger than or equal to than just at a point inside the interval. Right, so I evaluated at c, it's got to be less than or equal to the maximum over an interval that contains the point. So this is actually the version that we're going to work with now for Taylor's inequality. But just to show you that the one I showed you earlier wasn't just crazy, I could say this is less than or equal than the maximum over an even bigger interval. So I'm going to say x minus a is less than ROC of the same thing here, and the variable is actually x in this one. But that's okay. These are all just dummy variables, and by dummy variable I just mean it's the variable for whatever the max, because we're trying to find the max over it. So it doesn't really matter what number I use here or what variable I use here. I could pick c and pick c here as well, but I just wanted to be consistent with the slides that I showed you before. And so let's show that this is true. So the maximum over this interval, so this thing here, the maximum over this interval is this point right here. So that has to be less than or equal than the maximum over this interval, which happens to be over here, and that's true. So in my slides originally, in the Taylor's inequality, I said pick m to be bigger than this, mk plus 1 to be bigger than this. Instead, we're going to choose mk plus 1 to be bigger than this, and this will still be true when we write out the step down here. So this following step. So don't mind the stuff on the bottom. It's something I forgot to erase in a previous video. Anyway, so our k of x, well, it's equal to this thing, but it has to be less than or equal to the max of c belonging to a to x of f at the k plus 1 derivative of c all over k plus 1 factorial times x minus a to the k plus 1. Great. So now if I just pick this to be m, or pick m to be bigger than this, mk plus 1 to be bigger than that, then this would be true, right? This is less than or equal than mk plus 1 over k plus 1 factorial times x minus a to the k plus 1. And of course, mk plus 1 is bigger than the max over c from a to x of this thing here, right? The absolute value sign. And I'm actually running out of room here. K plus 1 evaluated at c. So this is where this version of Taylor's inequality comes from. I just want to pick m to be bigger than this thing here. And you can follow through the inequality. This all still works. And so the only thing that's changed in terms of the first Taylor's inequality that I've shown you, and this one, is that how we pick m of k plus 1. So we're saying pick m of k plus 1 between a and x. You'll notice here that I picked x to be bigger than a, and this is just a convenient way for me to write it, but there's no reason why it should necessarily be like that. In fact, if x is smaller than a, then you would just write c is between x and a, like that. So you pick the one that works depending on how you pick x and a. So in my next video, I'm going to talk about how to do 7b using this new version of Taylor's inequality. So the only thing that's changed is how I pick m of k plus 1. I pick it to be bigger than this middle thing, and not the one I had originally, this one. Okay, great. Let me know if you have any questions. Post some comments. Let me know.